let's get started for the afternoon session with Shmoys from Cornell talking about this really interesting Citi bike project.
Great. Thanks, Steve. And thanks to the organizers for this chance to come talk about this work here and have a great time the rest of the week as well. So, bike sharing systems are starting to be a regular part of the urban landscape. There are really, at this point, hundreds of cities in which such a system is present. So what is a bike sharing system? For those of you who might not have encountered it, it's in this case, it's a map of Manhattan with a footprint of stations. You see one such station in the background behind that map of a collection of docks on the one hand, and bikes filling those stations. And a rider can pick up a bike at any given station and return it to any other station of his or her choosing. And of course, what?
Is he a smoking, the biker, or like
no. There's a cell phone. It's DiCaprio. Now, and actually, let's truth in advertising. So there are two Citi bike systems, one in Miami and one in New York. He is on. You can tell from the vegetation, the one in Miami, not the one in New York. The main operational challenge, though there are many operational challenges in running a bike sharing system, is that of imbalance. That on the one hand, you can see a station left where a rider is about to return his bike, and it's not clear where he's going to pick it up. And on the other hand, the woman on the right sees nothing but empty docks. And you get, when you work with companies like this, you get, irate messages like the following. That's a literal one. That even when I just now have the associated, this came to my email account, not even to Citi Bike. Check out the problems. So to give you a sense of a day in the life of a bike sharing system, I'm going to play you a movie now. This is a couple years old, so. It's not accurate for the current time, but it'll give you a feel for the way things are. You'll see on the upper left there'll be a clock that tells you the 24-hour time. So we're going to start at midnight when things are pretty quiescent. That for each station, the volume in a given short time interval will be depicted in terms of the net flow by the diameter, and if it's net flow departing, it'll be red. If it's net flow arriving, it'll be blue. And let's go to the video. So it's, this is the city that never sleeps. Indeed, you still see, even in the wee hours of the morning, some scattered activity. Without any real sense of pattern to it. But now it's getting to be 6, and all of a sudden the city comes to life. That you see a lot of red here in the East Village, a lot of blue here in the financial district. The traders are waking up and taking their bike and going to work. It's now 10 o'clock, things are calming down. Now comes lunchtime, and there's a little burst of activity, and the patterns of what's blue and what's red somewhat different. Now lunchtime has faded, it's calmer a bit, and now we're picking up into the rush hour. By 4 o'clock, things really start to be heavy, and notice that it's the asymmetric version of that the financial district is red and the East Village is blue. But there are interesting anomalies that it's still pretty heavy till about 8 o'clock. And then we back down to the evening, and little by little we make our way back to midnight, when things are now calming down a bit. So this is as I said, a bit old, but really gives you a flavor for the way things are, and things haven't really changed. To give you an order of magnitude of scale, last month, the month of May, there were more than 1.2 million trips taken. There are. Depends how honest I want to be. There's something like, over that month of May, the number of bikes in service went from 6,000 up till about 7,000 over the course of that month. I'm not at liberty to tell you why there was that gradient there, but well, I can tell that they had some issues with maintenance, and they had to pull 2,000 bikes off the road at the beginning of April to do systematic repairs for a very troubling reason, but that's all behind.
How many bikes and how many stations are there?
So there are so let's say today there are something like 7,000 bikes on the road. There are something like 14,500 docks and roughly 400 slightly plus stations in the current footprint.
Only Manhattan, or does it go to?
So you'll see more current maps that there's a good swath of Brooklyn and a little piece of Queens that's currently there. And when I was there 2 weeks ago, there are rumors that it will be expanded to be fully citywide. But that's a substantial capital investment, and there are interesting discussions as to where that capital will come from.
All the way up to Columbia.
Columbia, I would be astonished if it isn't there in June. I mean, not this June, but a year from now. A year from now, there and yeah, yes. So you, yes, good. So sort of heaviest, sort of key points of thinking about this data. I mean, one of the nice things about these systems is that we have a complete record of everything that happens. So here we go. A user to use the system, has this pass that you stick into the dock. It releases the bike, so it records. I mean, your ID is embedded in this, so the system knows the ID of the person using that bike. It has an ID for the bike that is docked, that has an RFID chip in the handlebar tube structure of the bike. There's a dock ID, so we know exactly which bike is being removed from which dock at a given station and at what time. And then, contrary to rumors, there has never been GPS devices on at least New York City's bikes. So the only thing that we know is when that bike then reemerges at another station and gets docked in. And indeed, sometimes, as not surprising, it doesn't ever reemerge. And then the person's credit card gets charged a hefty chunk of change. Okay, so we know.
Information 100% reliable?
No. Even though it's billing data, it is still not 100% reliable. But it's pretty good. It's yeah. So most trips are by commuters. That's not the same thing as saying that most trips are commuting, which is still true, but indeed people who use it regularly for commuting then also use it for additional trips throughout the day. So it's not unusual to see a person making on the order of 20 trips a week as opposed to just the 10 commuting trips that you would expect. Yeah.
When you say most trips by commuters, what do you mean by commuters?
So we believe that they're taking it from their residence from their residence or some transit point on their travel to ending up at work, and because of timing information, it occurs somewhere between 6 and 10 a.m. and then we see symmetrically from that leaving from one of the stations near where they docked it in pretty much the reverse direction. That's what I mean. As you saw on the movie, the heaviest use is between 6 and 10 a.m. in the morning and between 4 and 8 p.m. What's not immediately visible, but what the data shows is that it's heavier in the afternoon by and large than it is in the morning. That's maybe not so surprising. People don't want to arrive sweaty to work, and depending on the particular commute route, it may actually be slightly less efficient. Some places one of the big corridors is that East Village to the financial district, and that probably is other than taxi, the most efficient way of going between the East Village and the financial district. And so it's not surprising that it's complementing the traditional built-in infrastructure in city public transit. And so really the central question that we want to build models is if we think about, we're not going to have much ability to influence where bikes are during the rush hour, because any transit of bikes by vehicles during rush hour has the same limitations of what Manhattan is like. So the main question is, as I think about it, what do I want as stocking levels at the start of a rush hour? Or in particular, what I want as a stocking level at 6 a.m. We'll talk about other things that are done to sort of mitigate the fact that how you actually satisfy demand over those heavy usage times. But that's the first question that I want build a model to do. And at this point, the models that we have for around the clock targeted inventory levels are what actually the city uses for defining what it thinks the right amount at a given station at a given time. And as much as we set these target levels, they aren't achieved. I mean, there just isn't the operational costs in achieving these target levels far exceed what would be reasonable for them to do, and so there are various compromises that get made. And we've been working on models to figure out exactly quantifiable ways to deal with exactly those trade-offs. So here's the basic framework that we're going to take a step back, that thinking about this data in the aggregate means that we can make some simplifying assumptions. You can use historical data to approximate both the arrival traffic for picking up a bike and the leaving off traffic for depositing a bike as Poisson flows. And we'll make the reasonable but perhaps not so reasonable, we can come talk about that later, that these are independent rates. And so this means that, just to sort of get you thinking about what the issue is, that if we know that there's a lot of flow from Penn Station to the East 30s, then if Penn Station is out of bikes, then of course that's going to affect the arrival rate as well. So they're not independent, but for a first approximation, we're going to assume that. And the idea that we're going to use, the guiding metric that we've used throughout all of our models, is that we want to minimize the expected number of people that arrive either to rent and there are no bikes, or the number of people who arrive to return and there are no docks, and the sum of those. Okay, so that's the objective function. We want to minimize the expected value of that objective.
Isn't one much worse than the other?
Yes, one is much worse than the other. On the other hand, if you have a bike and there isn't a dock, you will solve it. You are on wheels. You'll go and you'll ride it to a nearby station. And indeed, many of the things that we've done has moved the city from thinking about the quality of service metrics from being targeted by stations, but by actually thinking about neighborhoods, so as to be sure that those kinds of trade-offs get taken into account. So we're going to, more explicitly, we're going to have a continuous time Markov chain model that ranging, the states of the Markov chain will range from that the station is empty to the station is fully at capacity in terms of the number of bikes, and that there are going to be transitions depending on the arrival and return. Arrival of renters and the return of bikes there, and that's, if lambda is the rental rate and mu is the return rate, we're going to have a cost associated with stocking, let's say at 6 a.m. And think about the planning cycle of an 18-hour, or let's say a 4-hour planning cycle through the rush hour, of the cost of the expected number of upset people, given that we've stocked the station initially at I. So a little bit of notation, if x of t denotes the state at times t, it's somewhere between 0 and a given capacity c. And then if I just focus on one of those two terms, we're going to compute the expected value of the flow rate out. This is an indicator of that currently the state is empty, given that the chain started in initial state I. And there's a symmetric term, of course, for.
Use continuous time. Is it important to map events to actual time?
In terms of the computation, one could discretize time, but it only makes the computations underlying it messier. I know as computer scientists that it's a much more natural thing that we could sort of think about but essentially, otherwise you're going to be modeling a lot of self loops of things not changing, so if one thinks about that objective function, here are some of the cost curves from a variety of Sorry.
That's for one dock.
That's for one station. One station. So here I'm showing you a variety of different stations and different flow rates of what the expected number of customers who arrive without a dock, or a customer with a bike and want to return without a dock, or want to rent and there isn't a bike. So I mean, if you look at these curves, I mean, it's not no surprise. This is a convex function. That means that if I think about the system problem, I have a fleet of bikes, of total number of bikes B, and I want to minimize the overall upset cost of users across the system, and every allocation is going to be the number of bikes that I put at a given station S is going to be somewhere between 0 and the capacity of that station. Okay, so we have a convex optimization problem. In fact, one can prove, it's not hard to prove that in fact there's enough structure there that we get integer optima. It's just kind of a sort of convex allocation problem. And so we actually can solve this. In fact, what we end up doing to solve it is that we consider the lower envelope. I mean, the function is only interesting at integer values. So in fact, we sort of have a linear support underneath that convex function that we're really optimizing over. And so we're really solving a linear program and then being assured an integer optimum. Okay, so this gives you a sense of what we do, and we had been doing that. We'd been planning to think about the model over a 18-hour planning period, and that we would then be using where we are at the end of the day so this is at midnight, and this is the target. So this is load color coding, loads indicating of where we are, and this is what actually happens. And the color coding indicates whether we're close to the 6 a.m. optimum or not. And you'll see that while there is some improvement of what gets done by moving bikes overnight, it's not that the right map is turning white and that we're really getting close to the 6 a.m. targets in terms of what happens.
You can only find the optimum if you know what lambda and mu are going to be. How well can you predict those?
So the data gives us, so first of all, I mean, and I'll talk about this and I'll sort of steal my next slide or 2 slides down. I'm making, what I put there was as actually a constant rate Poisson process. And that's definitely not the case. And that really made a case that we were really thinking of planning through one rush hour, where we really thought that it was reasonable to plan. And I'm going to talk about going to time varying Poisson rates in a minute. And for that, there's an interesting question of censoring, in the sense that I know the demand that gets used, but I don't know the demand. I mean, especially on the rental, I don't know the people who didn't use the system because there wasn't availability. And the good thing is that we can actually, in some ways, de-censor the data by taking advantage of the fact that if I look at a given 10-minute time window and I just condition to understand the demand rate over periods when there actually were bikes available, that gives a more accurate estimate of latent demand. But overall, I mean, this is a human behavior thing, and people's behavior are being influenced by their general expectation of whether the service is available. And the extent to which it is getting used, I mean, I'm quite sure if we build it, they will come, kind of thing. There is, in effect, almost infinite demand at Penn Station. That, just to give you what actually happens on a given day now, is that every night we pull out of circulation an extra between 500 and 1,000 bikes. That's out of the total pool of 7,000. And they get stored in a depot immediately adjacent to Penn Station. Originally it was used to try to quickly shuttle bikes back and forth between that depot and the nearest legitimate station. And now they just set up a temporary station that people just come there. And it's an interesting process to watch. At what point during the morning does however many bikes they were able to pull out of the rest of the system does it exhaust? So what's the real demand? So what is the real demand? And that's an interesting sort of both estimation but also a behavior question in terms of how to really think about it. So the current ability to rebalance simply just doesn't move enough bikes. So one can ask another question of, now the way these stations are built, they're actually in modules of 2 and 3 of docks. So the fact that some original design decision was made in order to how many docks should be at a given station, we can actually go back to the same convex program, and instead of thinking about these as being input to the problem, we could think of them as being variables, and then there'll be an additional, budget constraint on the total number of docks in the system. And now we can ask the question of, are there better ways to allocate both bikes and docks together? And this was something that we did again for the constant rate, and we followed exactly the same framework. The math isn't as nice. We still have nice joint convexity now that we sort of have both bikes and docks and the kinds of variables that we're going to be interested in. Now the linear program that is sort of this lower envelope of the convex program, because in some sense there are 2 of these knapsack-like constraints, that we no longer have the integrality result. At least we don't know that we have the integrality result. From a practical point of view, when I solve that convex program, I get integers. So, and we'll see that at least from a complexity point of view, that's not so surprising that I'll talk in a minute about a direct combinatorial algorithm to solve that optimization problem. But another question is, is this, how much is our modeling assumption really affecting things? In particular, let's ask this question about the independent assumption about those rates being completely, stated as given without dependencies, as I think about it. So a natural way is to consider instead a simulation optimization perspective, and we can model exactly these stochastic processes and have a functioning system and see what kinds of performance we can get. And indeed, that we get better allocations of if I think about running the simulation on the optimized computed based on the static model. We can substantially improve it by doing some local optimization with respect to the original bike allocation. So this is just in the bike allocation mode. And so it's an interesting question of whether we can actually make the continuous time Markov chains better. And of course, another glaring piece is this was all back in the constant rate regime. Another thing to think about is that when you think about the difference between the simulation optimization model and what our cost curves give us is that one thing that we want is perhaps, and indeed how it's used, is while I focus by saying what's the right inventory at 6 a.m. and then we're going to use it through a given period of time, it's actually in terms of the day-to-day and real-time operations currently being used as I look at the system now and I can compute the analogous desired inventory level at a given snapshot within the day, how far off am I from what I believe the right inventory level are? And and this comes in the operation. And indeed, what again, the Twitter feed shows all kinds of people objecting to decisions that aren't quite the right thing. So let's look at some data just so we get a sense. So here I'm showing you a week or 5 days worth of plots at a station here at 27th and 1st Avenue. And on the y-axis, we have the number of bikes in a given station, and we have the 24-hour clock here. Okay? So one thing you can see is that, well, you can see the difference between weekdays and weekends in a very stark way. Here that's a weekend day, here we have a weekday. But even if I was thinking about the assumption that within a given rush hour, 6 to 10 a.m., I had constant rental and return rates, that's profoundly false for this station on a weekday. Now, yes, this is the worst station in the system for displaying the lack of that behavior. In fact, it's outside Bellevue Hospital, and what we're seeing, in all likelihood, is people arriving to work at 8 a.m. and then the overnight nursing shift and other parts of the hospital administration leaving, so that we have both inflows and outflows right from the same location, pretty much turning on at 8 o'clock. But nonetheless, if you look sort of station by station, the constant rate, even within a given rush hour, is questionable. So we don't see time invariant rates. Here's another station, Hudson and Reed. And actually this was the value that, if we think about, I mean, these are values set by the original morning rush dominated Markov chain. And one thing we just see is that although there are these large number of docks, we really just don't need that number of docks here. I mean, that the variability within a given day is not such that you're hitting both extremes, that you just sort of have a much more limited bandwidth of variability. So it's natural then to go ahead to a more sophisticated model where we're going to delineate the day into distinct time intervals, where just within that, let's say 30-minute time interval, we're going to assume a constant rate. But we want to then extend the same methodology to handle that. And of course, that will make the problem more complex, and that even just solving the linear program for that will be a stress on the system. So in some sense, there are three challenges. We want to generalize the time varying rates. There's this concern about the linear program versus the integer program when I'm thinking about both dock and bike. And I, for a variety of reasons, will want to have a more efficient running time. So this is the more general model that I now have a number of intervals across the day with different rates that will evolve. And I'm going to do a slight change of variables. I'm going to be thinking about, in an allocation, allocating a number of bikes in a station and a number of empty docks. Okay, so rather than thinking of it as the total number of docks, and they're just clearly a nice linear transformation. And so now the states will range between 0 and the total allocation full and empty docks. And we're going to have an analogous function. But we can extend the machinery by sort of standard stochastic dynamic programming in order to compute the cost functions over the course of a series of piecewise constant Poisson rates, because if I know the expected number of upset customers for any given station, for any given stocking level, then if I want to, for the last t minus k periods, and I want to extend that back to know for the last t minus k plus 1 periods, then I simply need to understand the probability of evolving from an input of B bikes to an input to a resulting state of beta bikes, and then the cost for the k minus 1 interval is the cost of everything from that interval on, plus the probabilistically weighted cost to go of that one interval. And of course, this was the things that we could compute for just one interval. And so it's just extending the same machinery in a nice dynamic programming kind of setting. So we can compute these cost functions, and now the clean and nice result is that, in fact, one can solve this simultaneous bike and dock allocation problem by a direct greedy algorithm of a somewhat non-trivial structure, but it's not too hard to prove. So the idea is that we initially put all stations there, no empty docks and no bikes anywhere. You have a pool of empty docks and a pool of bikes to allocate. While you have both bikes and dock, you find the best place to either put a bike in a dock in terms of improving your cost function, or the place an empty dock, wherever that's improvement. If in the end, what the thing that limits you of having both bikes and docks is you have no docks left, you end. Otherwise, you still have additional docks. You either add an empty dock or together take an empty dock with moving one of the existing bikes wherever you get the most improvement. So here's maybe rather than words, pictures probably work better. Initially, you haven't allocated anything anywhere. You have a collection of bikes and a collection of docks. And either you're going to allocate an empty dock or a bike and a dock to a station wherever the improvement in the overall cost of the system is greatest. There are two ways in which this will end, where you have docks left but no bikes, or bikes left when you have no docks. In the first case, you check, well, what can I do to improve the system by allocating an additional empty dock to one of my stations, or if I allocate one of those docks and I move a bike from where it currently is and leave that empty dock somewhere else. Okay?
Are you saying this is the realistic model for the design, or actually for operations where you can actually move empty docks at various?
So this is first of all, this is an algorithm to solve in polynomial time the stochastic optimization problem of choosing the best allocation of bikes and docks system-wide, okay? So this is something that, given an annual review, the system goes down basically in the winter months, when one could do movements of bikes from the docks from the current configuration to next year's configuration.
It's not that you run this every night and you move
No,
the docks.
this is the moving docks is it's a hundreds of pounds kind of thing. You need a crane to lift it up. This is move a small number of docks.
Also, every square foot in Manhattan is spoken for. How do you add a dock somewhere?
So one has to actually add box constraints on what for every given station. What's the limit on the size of that station, and that's doable as well within the same framework. And if you only have bikes left, then you terminate. The key thing, I won't go into it, is a kind of two-dimensional version of submodularity that holds for functions of this sort. That is a concept known as multimodularity that was introduced by Bruce Hayek. I won't go through the underlying mathematics of that, but nonetheless, this is sort of the structural property of what our cost functions have and it has essentially the decreasing marginal returns in a number, in fact, 3 different dimensions, even though there are only 2 explicitly here. And I won't talk about the proof at all. But claim that indeed it's not too hard to show that the algorithm that I just described does produce the optimal allocation. So we've gone from a setting where we were thinking about things in terms of constant Poisson rates versus this time-varying Poisson rates, and also the sort of questions of both, are we just allocating bikes, or are we allocating bikes and docks? Simulation optimization improved the bike allocations in the constant rate. What happens here, now we've improved in 2 dimensions. It's really thinking about both the bike and dock allocation and the fact that we have time varying Poisson rates. The analogous simulation optimization, rather than before we got 20% improvement, now we could only get 3% improvement. And of course, the fact that we're using it, running this greedy algorithm rather than solving this LP, we're using about 2% of the running time in order to actually compute the results. The second example I showed you, which was somehow not being managed right, is an interesting case in that it's very clear that although you're allocating this large number of docks, they're not really getting used. And one thing that highlighted for us, and I'll loop back to this, is one can try to understand that in operating the system, Motivate spends a tremendous amount of money moving bikes overnight. And one can ask the question of, is it worth it? you don't make that much in the way of improvements. Now, one has to be very careful in building that model because things like this depot outside Penn Station play a critical role in terms of the performance of the system. But one thing you can compare it to is what I'd call a steady state analysis. So as you think about this model, rather than just running it for one 18-hour period from 6 a.m. to 12 midnight, and I'm trying to understand how that system evolves and what the costs are, now just repeat ad infinitum. How would the system work and evolve? In terms of thinking about solving what's going on, we can really extend the same kinds of tools. And we can even think about really what's happening. This is as an embedded Markov chain for which we understand the limiting distribution, and can therefore do the cost analysis. So here's a table that compares a number of strategies in terms of what the optimization results show. So on the one hand, if we optimally allocate bikes and docks, and we do the full rebalancing between 12 midnight and 6 a.m., which is tremendously expensive, the expected number of upset customers in the next 18 hours is something around 9,300. Okay. In contrast to that, if I allocate bikes and docks according to what the steady state behavior looks like, and I do no rebalancing, I just initialize the system, but I've allocated the docks in anticipation that I'm not going to do any rebalancing, I'm at 11,000. But to give a sense of how bad the current allocation is, even if I did optimal rebalancing, so I did absolutely everything, for the way the docks are currently laid out in terms of where they are in the city, I have 12,000 expected upset customers on a daily basis. So doing nothing in rebalancing for the right configuration of docks gives me better performance than doing absolutely perfect rebalancing for what the system currently has. And of course, we're currently trying to nudge Citi Bike to sort of grapple with the fact that they may want to do the political wars of what it's needed of what it would mean to actually move to that dock allocation from where things currently are.
Is this a daily number?
This is a daily number. Yeah.
That's a lot of.
That's a lot of. So the system is very strapped. The system is really under capacity. That's another important takeaway. The system is undercapacitated in a huge way.
But another way of saying that, the system is undercapacitated, i.e. there is massive demand, i.e. even if you treat your people badly, you're going to get lots of customers.
Yes. So the question is, if I treat them twice as badly, should I really care? No, that's...
When you talk about daily rebalancing, what would be the cost in dollars of rebalancing? And I guess to relate that to the cost of unhappy customers, do they view the revenue from people hiring them as a revenue stream, or do they just view it as peanuts compared to the benefit on the transit network of the city? So
first of all, an important, and I'm badly misjudging time, so I'll try to. So one important thing is this is a private profit-seeking entity that has a quality of service contract with the City of New York. So the question of their goal as a company is to make sure there are enough subscribers to help pay the bills. Now, there's an understanding that the same umbrella company, Motivate, runs bike sharing companies in a large number of North American cities. The investors are actually based in New York, and they care more about the performance in New York, and are willing to let New York be a loss leader in terms of what operations do. But to move one bike, and then I'll say a little bit about incentives and other sorts of things of there. To move one bike costs at least $1 per bike moved. So it's very expensive. And in contrast to that, an annual subscriber for all you can eat, and I'll put that up in a second, pays $155 for the full year's usage. So there's no question that there are a whole host of users that are, for whom their annual subscription does not pay the rebalancing cost just for their own use, let alone the actual physical entity of
What I don't understand is why people actually use this service. I mean,
as opposed to buying them.
buying the bike.
So the expected cost of a bike in New York is pretty high because it gets stolen. You also don't have room to put it in your apartment. And what's more, it involves, and perhaps the fundamental thing that makes it really important is it allows different modes of transit in different directions. Yes.
I use a bike share in Philadelphia. If it's going to rain in the morning, I walk or take a bus, and then it's nice. I come back.
I mean, our operational nightmare is the very rare summer late afternoon thunderstorm, which of course isn't there because it means that you've had this tremendously asymmetric flow, which puts bikes, where people work, and then all of a sudden nobody rides it going back because and somehow or other something has to be done overnight, and really what happens is not so much.
There's a similar service in Tel Aviv, but when it was a novelty, it was used a lot, and then demand just decayed.
So a typical bike in New York, gets used 8 times on average. No. Per day. That's. So, for example, one thing. So if you look at the steady state analysis that we did, and we ask where does that, don't worry about rebalancing, but to get the dock allocation right. Red means take out docks, blue means put more docks there. This is politically impossible. It just means essentially strip Brooklyn of all of Ed Queens of all of its docks because it's just not getting the same level of usage. But nonetheless, it's really, you could maybe say that where this is just a political investment, the real question is, what would it take in terms of additional docks to bring the Manhattan levels to that point?
I don't want to eat your time, but that's an interesting point. Movable stations, okay?
Yeah.
The point is that, I heard this Coke guy talk about the congestion costs are so high and the warehouse costs are so high, they're moving warehouses.
Mm-hmm.
One of the 18-wheeler trucks that drives through Sao Paulo, and a motorcycle goes,
So we do it. So there's a notion of a corral, which its first there are things that are called valets and corrals. The first implementation were either chain bikes to a tree and have someone there to actually be able to extend the capacity of a station. The more sophisticated things are called corrals, where in effect, because if you looked at the pictures, there's a fair amount of space between there, and so again, if you have an attendant,
just have bikes inside trucks.
Yeah.
Bring the trucks in.
So those are our movable depots. We know that there are. The old post office building is what gets used as a piece for this large number of bikes that are handled opposite the Penn Station, but there aren't equally things. But a box truck of 50 is only a box truck of 50, and within rush hour, moving those box trucks of capacity 50 is itself limiting. So you can about double the capacity by having a movable station. You can about double the capacity, and you want to do it at a station because it's going to take an attendant in order to actually handle that. So aligning it with there already are stations, and what the map means is psychologically a better thing. But all of these games have been played to try to have more variable capacity.
You could have a 3D printer printing new bikes.
So in my non-existent time, let me say, so this was mostly about the operations of just trying to understand, have a good model for how many bikes should be at a station at a given time, but there are a variety of other interesting operational questions. If we're going to do overnight routing, how do you actually do that efficiently? And that's just an interesting new model of a vehicle routing problem. The first version, when they had really bad crews, the crews could not take any instruction about how many bikes to pick up and how many bikes to drop off. So we ended up giving them simpler instructions, which were just fill the truck with bikes from that station, drive to this station and empty the truck and put all of the bikes there. So that was our overnight rebalancing one. The crews have gotten better, so we can give them more sophisticated feeds. The way in which mid-rush rebalancing gets handled predominantly is that they built bicycle trailers, so a pedicab that can hold 5 or 6 city bikes on its back, and then can be bicycled back and forth between 2 nearby stations, one which has too many bikes and one which has too few, and then we just designate pairings and they go back and forth. And so there were nice facility location style optimization problems that can get solved to determine how that gets done. I mentioned these corrals of putting additional people so that you have this movable extra capacity. How you actually, when you have the ability to have a few of them, how do you place them is something that we've worked with them on. And then one thing that's really just in the last 6 weeks, there's now a Bike Angels program and this is by far and away the most likely to change bad finances to a workable model, is incentive schemes to get around the fact that the city's pricing framework is as dumb as can be, in that it's just all driven by annual thing. So just to give you a sense, this is the current pricing scheme. You can pay $12 for a one-day pass or $24 for a 3-day pass. You can ride for 30 minutes for free for those, and then to take as many rides afterwards, or $155 for really everything you want. So those traders in the East Village that are commuting to the financial district are getting quarter rides for their commute rather than $275 what it takes to ride the subway. So yeah, and this is what I mentioned before, that rebalancing alone exceeds. If you look at sort of the usual 80-20 curve, the 20% of the subscribers are doing 80%, and actually it's more like 10 and 90. The 10% of the users are doing 90% of the rides. Those 10% are not paying for their rebalancing costs alone. In time that I don't have, I'll just allude to stuff that Sid won't be talking about, but recent work with 2 Cornell students on some demand-driven pricing models, which I guess you can ask either of us about in the break. There are a number of ongoing things. One thing that there's sort of this myth that for every the ratio of docks in the system to bikes should be 2 to 1. Every system is set up pretty much with that ratio. There's no scientific basis for this whatsoever. And in particular, in a model where you're pulling depots out, so you can have a way of sort of putting additional capacity in a surge way, it's clear that that's not the right thing. So that's one nice thing of how to use our simulation optimization tools. There are crazy operational things. So in New York, the stations run on solar power, as opposed to in Tel Aviv, where they're on the grid, which of course makes no sense whatsoever. So this means that the 2 car batteries, like things which really don't get recharged by solar, have to be replaced on somewhere between 2 to 3 week intervals. And just actually maintaining that piece is an interesting operational challenge in terms of keeping the system going. We're giving them new tools to do better overnight rebalancing now that their crews do better. And one really nice problem that's evolved over, and we've given them some help on, and there's better things to be done, is that when a bike moves into a dock, there's a handshake protocol to pin that bike into the dock, okay? So, and there's really detailed information about what happens and when there's an attempt and whether it actually succeeds. But you have this very sparse set of triples of dock ID, bike ID, and user ID. And when you have failures like this, then you're trying to, I mean, are you supposed to find that bike and pull it out of circulation? Are you supposed to go and plug and play the new dock? Or are you supposed to send the user a new instructional video by email so they do a better job of actually locking their bike into place? And actually trying to make headway with that data is a sort of an interesting thing we've been working on recently. I mean, in general, this is just ripe for a range of data, analytic questions. But the message I want to conclude with is sort of tying it back to real-time decision-making is that having the model to know a measure for thinking about how many bikes should be at each station is really sort of the groundwork for then being able to do the kind of real-time decision-making that now actually gets done by hand, of a dispatcher recognizing that a station is way off from where it should be, and then we give them an automatic tool to say where should you be pulling bikes and sending a crew to pull the bikes from the current system out and replenish the stuff. So that gives you a sense of a range of different things we've been doing, and I'm happy to take questions.
Yeah, you kind of mentioned about incentivization part. So I guess you essentially always need one bike and one free space in each station, and then essentially the problem solved. So could you sort of charge, there's two questions I had. So one is I guess you could just charge based on occupancy, and then you're paying the price of the person whose bike.
So this is why incentives are such an important mechanism, in that this is a contract that Motivate has with the City of New York. The annual subscription fee of $100 and some odd for all you can eat will not go away. This will be part of the contract come hell or high water, or at least until there's a very different administration. So then incentives gives the mechanism for introducing in effect an alternative currency. And really what you want to do is you want to shape behavior. So, if you could, if you think, one of the ways in which the city is different than most cities is that the cobbling between residential and commercial is much more intertwined. And so you do have lots of pairs of nearby stations where one is saturated with bikes and one is starved. So, it's not Singapore where we can, promote the healthiness of walking that last block, but if we can, still provide the incentive so that people can, if nothing else, get that over time their subscription is paid, or then that gives a way of doing that. Yeah.
The second question is why don't you just overcapacitate the system in terms of numbers of bikes, rather than moving overnight, just
so you have to be careful.
Take half the bikes out, just remove them from the network, overcapacitate, so then they still come through the next half. But you just take bikes out of the network.
So there is a delicate balancing act, though, that just as the first footprint that I showed you in the movie only went up to 57th Street. And the new bikes for the further expansion into Queens and Brooklyn and up the Upper East Side and West Side actually arrived before the expansion was complete. And so there was a brief period where they had more bikes than this 2-to-1 ratio. But what then was happening is that there were many more instances of the two docks for every one bike.
Yeah. Why not have 3 bikes for every 2 docks and then just take them out at rush hour?
Well, so you have to be able. What do you do? And where do they go, right? So the point is that someone pointed out that it's not symmetric in terms of how upset a person is if they arrive and there's no bike. They'll just take public transit. But if they've got this bike and they've got to get rid of it, and there isn't anything in the neighborhood, and this has, it's not like this is a rare phenomenon.
It's unpredictable demand going from one side to the other. You can just say, let's have 3 times as many bikes as there are docks.
But there is...
Vans come up rather than over the night. Vans just come up during the day, take out those.
But there is all kinds of predictable stochasticity, right? So I know when the storms are coming. So I'm going to leave work earlier to be able to bike there. All of a sudden, you get this surge of traffic, which you then have to be coordinating with in real time.
So are docks expensive?
Yeah.
And
everything's expensive.
More expensive than bikes? You could just
No, they're cheap. They're
put a lot of dollars.
Oh, no, you can't. Sorry, that's real estate. That comes from the city. I mean, what is the city? I mean, the company has a QoS contract with Citi. What are they getting from the city? They're getting the real estate on which to put those things.
Well,
So
they could build second.
yeah, I mean, in effect, that's what they're doing with these corrals. But
I think the other, thing about the bike sharing programs, in the case of New York City, it started out with Citibank putting the first $100 million for the advertisement space that these
40.
stations gave them, right?
40 million.
40 million.
40 million.
But then for 100. Okay. Everybody thinks it's 100 by the way.
So the second round was another 60. So it's 100 between the two. Right.
So the thing is, what I'm getting at is that if you look for sponsors for incentive programs, we talked briefly about this, but when I spoke to the Citibank folks, I was suggesting that mix tickets and various things like this. That would be quite powerful motivators.
I mean, in fact, one thing which I don't understand why their marketing department isn't better is that the one idea that we gave them is that it's easy to identify large employers that are in anti-flow locations. If we could, we would be happy to, for a very small fee, that is really nothing, give employees, memberships, provided that those are sort of restricted memberships, that they can use it to go to and from work. So you can't use it to go to work as much, but you can certainly use it from work.
The point I was also making is that the same advantage Citibank saw, namely the advertisement value of supporting wellness type things, and the ubiquitous.
The new round of investors, I always forget the name, but it's this very upscale health club. And that was their intent in adding the second round of capital, was that they thought they were going to integrate it within their health club regime. But yeah, I mean, that's certainly an important piece. But maybe I should let people have a break and take questions offline.
Okay, thank you very much. Oh, is there a break now?
There's a break now.
Oh, okay.